Molecular geometry. What is molecular geometry? It is a description of the three-dimensional arrangement of atoms within a molecule. What kinds of positions does the atoms take inside a molecule? What final shape do they together take? So the shapes of molecules is the molecular geometry. Why do we need to study this? That's because the shape of molecules is related to the physical and chemical behavior of a substance. That's why we need to study that. Keep in mind, two atoms can only bond together if they have electron pairs shared in between them. So atoms can only link together if they have electrons in between that are being shared, be it a single bond, double bond, triple bond. Keep this in mind. Because of this, let's do things a little bit differently this time. Okay, starting from now on, let's treat each atom in a molecule as a little creature, something that can move around and do something with other creatures. All right? And these little creatures, a few of them together, they can make a team. A team of creatures will be like a molecule of a few atoms. Our job is to find out the pattern or the shape they can make when a few little creatures form a team. Okay, so we have a few individual atoms. We treat them as little creatures now. Some of them will stay together to form a team, and their team, they have specific positions for each creature to take, so they may make some unique patterns. Our job is to find out the shape or the pattern each team can make. Before that, let's make some assumptions. Number one, when two of them hold hands, we say that is actually a chemical bond. Okay, they're two little creatures. If they have a chemical bond, we say they are holding hands. Holding hands could be through a single bond, double bond, or triple bond. One of the little creatures inside a molecule or inside a team will be at the center. All right. In the Lewis structure procedure, in the last lecture, basically, we realized that majority of the molecules structures we talk about, most of them, there will be an atom in the center. All other atoms will be around that center atom. So here we go. If that's the case, we will assume inside the molecule there is one little creature will stay at the center. All other little creatures will form a team by binding to it, by holding hands with it from outside around it. Another assumption, the center, okay, that center creature may have different number of hands. Depending on who is in the center, that one may have 2 hands, 3 hands, 4 hands. And it may not hold all of its hands with other little creatures. Well, the center creature, for example, may have 4 hands, while it may use only 3 of the 4 hands, holding with other 3 team members. The hand number 4 maybe just left there free, not doing anything. Okay? So let's assume that. So there's a situation where a center may hold hand with 3 other things. There may be another hand staying here not doing anything. Okay? Now, here's the important statement. The locations of the hands from the center decides the final shape or the pattern of the team. What does that mean? For example, this is the center atom or the center creature. This one is going to hold hands with two other little creatures. Well, remember, the other two little creatures can only get connected with the center through holding hands. So if the center gave its two hands like this, then the two other creatures can only come from this direction. If the center gave its hands to the two other creatures like this, then the other two creatures can only hold hands with it from this direction. Now, depending on where the center will offer its hands, the final shape of the team will be different. This team will be an angular shape. This team will be a linear shape. Does it make sense to you? The locations of the hands from the center decides the final shape of the team. The other team members can only connect to the center from where it has hands. We just talked about this. Now, how do I know the locations of the hands from the center creatures now? Okay, we understand if we see the location, we understand the final shape, but how do we know the locations of the hands? Well, here is another important assumption we will make. The hands from the center creature, the center atom, will stay as far away from each other as possible. These hands from the center atom, the center creature, they don't like each other. They fight each other. Okay? They push around, they repel each other. As a result, they will stay as far away as possible from each other. Hopefully, when we are talking about this, you kind of realize that, oh, it actually makes sense because the hands of the little creatures are actually electrons. And electrons will repel each other because they all carry negative charges. All right, let's move on. Let's try. Our next job is to find out the location of the hands of the little creatures. Remember, the key is that the hands from a creature will push around each other, will stay as far away from each other as possible. That's our final goal. But right now, we need to do this. Find the locations of the hands from the center creature. And here is the reminder. Remember, the hands for the little creature will be as far away as possible from each other. Okay, now let's look at the situations. If the center creature has two hands, then the two hands will stay at the opposite sides of the creature. That's the farthest away they can stay. Make sense to you? Okay, they will stay as far away as possible to each other, so the two hands will be totally opposite from each other. On the other, each one is on the other side from the little creature, the center atom. We call this geometry, the shape of two hands, a linear geometry. Okay, these two hands will be arranged around the center in a linear shape. What if the center has three hands? Think about three hands on a little creature and they're pushing around, they're fighting around, they repel each other. Finally, they will take a final balanced position, nowhere to move. And that shape will look like this. None of them could move away from this position. The three hands will be in the same plane. They're in the same plane. If they move out of the plane, it will push back by the other two hands. So, and each angle is even 120. this shape or this arrangement of the hands is called trigonal planar arrangement. All hands are in the same plane. They are equally separated from each other. The angle between each two hands will be 120 degrees. What about 4? What about if the little creature at the center has 4 hands? Now think about it. This is kind of hard to describe or to think about. But let me show you the final positions of the 4 hands. That's where they will be, all balanced out. All right? It will be at the center. They will form a geometry, a shape with 4 surfaces. One surface here, one surface here. There's another surface towards the back. There's another surface at the bottom. So this shape is called tetrahedral arrangement. Okay, we have actually 3 possible arrangements of the hands from the center little creature. Depending on how many hands it has, it may take different arrangements. Now here is our goal now. I hope we all realize that our next step will be trying to figure out how many hands does the center creature have? How do we know that? Or if we are talking about a molecule, the question will be how many electron groups are there around the center atom? We are focusing on the center right now. Reciprocal theory is the tool we can use to figure out how many hands are there for the little creature in the center, or how many electron groups are there on the center atom. Reciprocal is the shortened form for valence shell electron pair repulsion. Well, I don't like the electron pair very much. Let's consider it as electron group. Valence shell electron group repulsion. What is it? Basically, it is just telling you around an atom, regardless of how many groups of electrons are there, they will push each other, they will repel each other and take their final balanced position. Basically, each group of electrons is a hand for the little creature. We can use this theory. This theory provides us a set of procedures for predicting the geometry of a molecule. To be exact, is to predict the electron group arrangement of a molecule, of the center atom. Using information contained in the molecule's Lewis structure. Oh, we need to do this. We need the Lewis structure of the molecule in order to predict the electron group arrangement around the center atom. Let me repeat that again. In order to predict the electron group arrangement around the center atom, we need to know the Lewis structure. And one more time, why do we even need to know that? Because that arrangement decides the final geometry of the molecule. Remember that. The position of the hands from the center little creature decides the final shape of the team of those little creatures. So let's see. The electron group arrangement around a given atom, we're talking about the center atom right now, is determined principally by minimizing electron pair or group repulsions. Yes, we went over all of this by talking about the little creatures. Now, we need to define what is an electron group. Okay, in the little creature's case, we say their hands. Here, we are saying, okay, electron groups. One electron group is a hand for the little creature. But what is an electron group? It is a collection of valence electrons present in a localized region around the center atom. To be exact, a single bond is considered an electron group. A double bond is considered an electron group. A triple bond is considered an electron group. Also, a lone pair non-bonding electrons. A pair of non-bonding electrons is also considered a group. Remember, we clarified earlier that little creature may have more hands than what it is using. There may be hands just staying there, not used. That will be a lone pair. Now let's look at how do I use Weisshaupt theory to predict the electron arrangement around the center atom, and finally to predict the molecular geometry. We are going to use all these molecules as example. 1, 2, 3, 4, 6 molecules as example. Step number 1. Draw the Lewis structure. All right, on the last slide, we clarified that in order to know the electron groups, you need to know the Lewis structure. So we're going to draw the Lewis structures for all of this. Here we go. The given time, I assume you'll be able to draw this. You should, okay? If you don't know how to draw them, go back to the last lecture, go through the steps for the Lewis structure drawing procedures. All right, we have all of this. Now, number 2, determine the number of electron groups and determine the electron group arrangement around the center atom, of course. All right, it is asking us to do 2 things. Number 1, decide the number of electron groups. Then, number 2, decide the electron group arrangement. Okay, let's work on the first one together. Double bond is a group. We're focusing on the center atom, remember? We're focusing on the center atom. Double bond is a group. Double bond is a group. This center atom has 2 groups. If the little creature has 2 hands and these 2 hands are pushing around each other, remember the final arrangement of the hands? Linear. Do you remember that? That what was our conclusion before? So the electron arrangement for carbon dioxide is linear. Okay, let's look at the second one, sulfur disulfide, sulfur dioxide. One group, double bonded group, single bond is a group, lone pair is a group. There are 3 groups of electrons around the center atom. Let's look at this one. The carbon is the center atom. 1 group, 2 group, 3 groups. All right. Both of these molecules, each one of them has 3 groups of electrons around the center atom. Do you remember the final arrangement of those electron groups? Trigonal planar. Trigonal planar. All right, they put only 2 electrons here. It doesn't matter if it's 2 or 4, okay, or triple bond in the future, but it has 3 groups. Now, if you look at the next 3, water, 1, 2, 3, 4, 4 groups. Nitrogen, 1, 2, 3, 4, 4 groups. Methane, 1, 2, 3, 4 groups. All right. There are electron arrangement geometry will be tetrahedral. We did all of this. All right. Now we know where the hands from the center atom are. Now we are going to connect either all of the hands or some of the hands to other atoms. Now let's predict what the final shape will be. Connect other atoms to the center. Predict the molecular geometry. All right. In the first one, there are two oxygens connected to the center carbon. There's an oxygen here. There's an oxygen here. The final shape will be linear. Make sense? Molecular geometry, linear. Oh, this is the same as the electron arrangement. Yes, in this case, it is the same because wherever you have electrons, you do have an atom there to take that position. They're bounded. So they are the same shape. Let's look at the second one. Let's look at formaldehyde. This is electron arrangement. Now, around each electron group, there is an atom, there's oxygen here, there's a hydrogen here, there's a hydrogen here. Well, the final geometry of the molecule will be the same again as the electron arrangement because everywhere you have electrons, there is an atom there to connect with the center atom. So the final geometry of the molecule is the same as the electron arrangement, trigonal planar. All right, now let's look at sulfur dioxide. It still has three groups of electrons around the sulfur, but only two of the three are connected to oxygen atoms. So there's oxygen here, there's oxygen here. The final shape, remember this is sulfur right now. The final shape, this is the final shape of the molecule. Three atoms forms an angle here. You may want to say, oh, what about that one? That's nothing. That's only a pair of electrons on sulfur. That is only an electron pair on sulfur. A hand that sulfur has but didn't use. So the final shape of this molecule is called angular. Three atoms forms an angle. Not only we know that, but also we know this angle must be somewhere around 120 degrees. Because those are where electrons are. Electrons are right here. Make sense? All right, let's look at the next one. Next one, we're going to look at methane first. I assume after the first two examples, you guys realize that, oh, this is easy. Wherever you have, in the case of methane, wherever you have electrons, you have a hydrogen atom. So the final molecular geometry will be the same as the electron arrangement. Absolutely correct. The final geometry of methane tetrahedral, the same as the electron arrangement, because wherever you have a hand, you have another atom linked, taking that position. The same. Ammonia. Ammonia, you have nitrogen here. Okay, you have nitrogen here on the top, right below nitrogen. You have three hydrogen here. All right. The whole thing is like a pyramid. Nitrogen will be the top of the pyramid. What about that? That's nothing. That is only a pair of electrons on nitrogen. So the whole thing is like this. Nitrogen here, hydrogen, 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 with a pair of electrons on nitrogen. That's the whole shape of the molecule. We call this shape trigonal pyramidal. It's like a pyramid. Okay, trigonal pyramidal. The last one, the last one is kind of easy. We have gone through something similar. Okay, out of the four electrons, out of the four hands from the center, only two of them are holding hands with hydrogen atoms. The three atoms forms a shape like this. Angular again. Not only we know the angle, but not only we know it is angular, but also we know the angle here between these two bonds, it should be somewhere around 109.5. 109.5 here it is written as 109. Typically, to be more exact, this angle in the tetrahedral geometry is 109.5 degree. Okay, not only we know that we will expect the angle from this hydrogen, carbon, oxygen, hydrogen, oxygen, hydrogen, this angle should be somewhere around 109.5. However, if you really want to know the true angle in reality, that angle is a little bit smaller than 109.5. Why is that? Because lone pair of electrons around the oxygen, they take bigger space than the bonded pair. So this bonded pair between, let me erase this, all of this. All right, this lone pair of electrons takes bigger space than these bonded pairs. The bonded pairs are limited between two nuclei. Lone pairs are right there with very few, with fewer limitation of this movement. So it takes bigger space. It pushed the bonded pair electrons downwards a little further. Therefore, the angle from hydrogen, oxygen, hydrogen, this angle basically is a little bit smaller than 109.5. Okay, let's have a quick summary to finish the procedures or the pattern we use when you try to figure out the molecular geometry of a molecule. Number one, you draw the loose structure. Assume I draw a loose structure of water. Okay, that's the loose structure of water I have here. And then what you do two things. Number one, figure out the number of electron groups around the center. And number two, predict the electron group arrangement. Well, I have 4 groups of electrons. 4 groups of electrons. The electron group arrangement will be tetrahedral. That's what it will be, the electron group arrangement. If there are only 2 groups of electrons, it will be linear. If there are 3 groups of electrons, it will be trigonal planar. Okay, so the number 2 is predict the number of electron groups around the center and predict the electron group arrangement. Number 3, connect other atoms to the center atom and predict the geometry. In this case, I'm going to connect 2 hydrogens. I'm going to come here. I'm going to connect 2 hydrogens to the electron groups, and that will be the shape of the molecule. Depending how many groups of electrons are connected, how many are not, the shapes could be different. Okay, in this case, in the case of water, I have 2 groups connected, 2 bonding groups and 2 non-bonding groups. 2 bonding groups, 2 non-bonding groups. These 2 groups are not bounded. The other 2 groups are bounded. There's hydrogen here. Depending on the molecules, it could have all 4 bounded. It could have 3 bounded, 1 non-bonding. In the case of this, you have different situations. Okay, it's a linear, you have only 1 situation. After that, based on your decision here, you predict the geometry right away. In my case, in our case, in the case of water, it will be angular. I hope you guys are following me. Molecules with more than 1 central atom. All right, we do not see this kind of molecules very often in this class. So let's quickly go through them. The molecular shape of molecules that contain more than one center atom can be obtained by considering each center atom separately and then combine them. All right, it is asking you to look at each center atom separately and then combine them together. So let's use these three molecules as example. So the first one is acetylene. There are two center atoms. Each one is a carbon. Let's look at the first carbon. First carbon has two groups of electrons around it. It's going to be linear. Two groups is going to be linear. Second carbon, two groups of electrons around it, linear. So the whole thing is a linear molecule. That's how the molecule look like. The whole thing, four atoms stand straight in the line. Okay. All right, the next one, hydrogen peroxide. The first center atom, oxygen, 1, 2, 3, 4 groups. 4 groups of electrons. The electron group arrangement is tetrahedral, but only 2 are connected to other atoms. One is hydrogen here, one is oxygen here. So only 2 are connected. So around this center atom, the shape will be an angular geometry. It will look like that. Same thing is true. If you do an analysis for that center atom, oxygen, it will look like that. So in this molecule, there are 2 angles, 2 bands in the chain. Well, if you do a similar analysis, you're going to realize this molecule has 1 band in the chain. Around this nitrogen, it is linear because it has only 2 electron groups around it. All right, we have gone through a lot today. Let's do some practices. Determine the shape and angles. Focus on the shape. If you couldn't predict the angles, look at the answer key later, and hopefully go over the previous couple slides. You'll be able to answer that. But your job is to figure out the shape and the bound angles for these 3 molecules. Okay, follow the steps laid out earlier. Okay, slow down, don't rush, don't miss anything. Draw the Lewis structure, predict the electron groups around the center atom, predict the electron arrangement around the center atom, start connecting outside atoms towards those electron groups, make the final decision on the molecular geometry. Slow down, repeatedly go back to the slides earlier. Once you're done with all 3, come back for the answer key. So pause the video and work on them. Check the answer keys later. All right, see you next time.